Hello and welcome to Additional Maths Lesson 26 with Mr. Barrow. Today we're going to be looking at exponential functions. In this chapter, chapter 12 of the textbook, it looks at exponentials and something called logarithms, which will be very new to all of you. And logarithms are ways of solving equations where the unknown is in the power. Okay, but before we get into that, we need to understand functions where the unknown is in the power. And these are called exponential functions. Okay, and before we go through that question that I have for you, let's discuss what exponential graphs look like. Okay, we're going to plot the graphs of y equals 2 to the power of x, y equals 3 to the power of x, and y equals a half to the power of x. And you'll get a general sense of what exponential functions look like on a graph. So in each of these functions, the unknown, the variable that we're going to be changing is in the exponent, or in the power, or in the index. So y equals 2 to the power of x, that is an exponential, a very simple exponential function. So the thing we are changing is the power. For every different value of x, y will be dependent upon 2 to the power of that value of x. So let's try and plot that. So if we plot some simple ones, 2 to the power of 1, that's 2. So when x is 1, y will be 2. When x is 2, y will be equal to 2 to the power of 2, which is y will equal 4. So when x is 2, y will be 4. Then when x is 3, y will be 2 to the power of 3, which will be 8, which goes off my graph. When x is 4, y will be 16. When x is 5, y will be 32, 64. It keeps doubling every time. We move 1 to the right. So as we increase in the x direction, the y coordinate increases exponentially. You will have heard that statement said many times, especially over the last year. That's what it means. For every increase in the x direction, your y increase is by a certain multiple. So every one increase in the x direction, we double the previous y value. That's an exponential. Exponentials don't need to be that steep, but that is a relatively steep one. Okay, doubling every time. Okay, not as steep as tripling every time, etc., but still, it's quite steep. Let's see what happens to it as we go to the left a little bit. Okay, so if we put in x as 0, y will equal 2 to the power of 0. Anything to the power of 0 is 1, so it'll go through that point there. When x is minus 1, y will equal 2 to the power of minus 1, which is 1 over 2 to the power of 1, which is a half. When x is minus 2, y is equal to 2 to the minus 2, which is a quarter. 2 to the minus 3 will be an eighth. 2 to the power of minus 4 will be a 16th, then a 32th, then a 64th. This will approach the x-axis, but it will never reach it. Even if we went all the way left to enormous negative numbers, so minus a million, 2 to the power of minus a million will be 1 divided by 2 to the power of a million, which will be an infinitesimally small number, but it will still be above the x-axis. It'll still be just a tiny bit above the x-axis. So the x-axis for an exponential function is called an asymptote. It's a value which the graph approaches but never reaches. So you will never get y equaling 0 for any of these functions, for any of these simple exponential functions. So let's draw the graph. So it'll look like this. Go through the points, and it'll have this shape. And it'll head off, doubling as we go in one more in the x direction. So that's 2 to the power of x. 3 to the power of x. Well, 3 cubed will be way off my graph. That'll be 27. 3 squared is off my graph. It's 9. 3 to the power of 1 is 3. 3 to the power of 0 is 1. 3 to the power of minus 1 is a third. 3 to the power of minus 2 is 1/9. 3 to the power of minus 3 is 1/27. So it'll be approaching the x-axis. It'll be closer to the x-axis than 2 to the power of. And it'll be approaching it but never reaching it, just like 2 to the power of. But on to the right of the y-axis, it'll be going up more quickly. It's more steep than 2 to the power of x because it'll be tripling. Every one movement in the x direction, it'll be tripling in the y direction. Next one, half to the power of x. Okay, half to the power of 3. If we cube a half, we get 1/8. If we square a half, we get a quarter. If we put a half to the power of 1, we get a half. Half to the power of 0 is 1. Half to the power of -1 is 1 divided by a half, so that'll be 2. Half to the power of -2 is 4. You might notice that it's very symmetrical and it matches one of the other two graphs. In fact, these two graphs, y equals 2 to the power of x and y equals a half to the power of x, are simply reflections in the y-axis. The reason for that is because a half to the power of x is actually 2 to the power of -1 to the power of x, which is 2 to the power of -x. And if you've worked in your GCSE course on transformations of graphs, you know that if this is our function of x, if 2 to the power of x is f of x, then 2 to the minus x would be f of minus x. And f of minus x is a reflection horizontally, or a reflection in the mirror line, which is the y-axis. Okay, so exponential functions do not always go up, don't always increase. These are exponential increasing functions, and the half to the power of x is an exponentially decreasing function. For every movement 1 to the right, we are halving the previous value. So we might see that in things like exponential decay, so radioactive elements, and so where if the half-life of an object was 7 minutes, then every 7 minutes, the previous mass of that object would be halved. Okay, you might find it in the value of a car over time. So if it loses 30% of its value every year, then each year, every one movement across in the x direction, you would find it would be 70% of the previous value because it drops by 30%. So those will be exponentially decreasing graphs. Exponentially increasing graphs will be things like putting some money into a savings account where it pays a specific level of interest every year. So every year you increase by a certain percentage. So year on year, you will be gaining amounts, and therefore the percentage on the new amount will be greater because it's the same percentage but of a greater amount, and therefore it'll be growing exponentially. And things like putting bacteria in a petri dish, and if they replicate, if they reproduce, if they double every 3 minutes, that sort of thing, then you will have an exponential growth. And you can model that using an exponential function. So we're going to look at two specific exponential functions. One I'm going to go through, and second one you're going to have a try. So first one, I invest £700 in a savings account. This savings account pays 5% PA interest. PA means per annum. So every year you get 5% increase on your investment as long as you don't spend any of the money or... Okay. So we want to write a formula for the value V of the investment at a time t years after investing. Okay, so hopefully you are relatively confident with using a decimal multiplier for increasing by a percentage. If I increase by 5% each year, then the decimal multiplier for that is 1.05. Because each year I will be gaining 5%, so I will have 105% of what I used to have. 105% as a decimal is 1.05. So if I wanted to know the amount I had after 1 year, it would be 700 times 1.05. If I wanted for 2 years, it would be 700 times 1.05 squared, etc. So the formula for the value of my investment, so V equals I start with 700 and I multiply it by 1.05 to the power of however many years I've had that investment. So that is a formula for the value, V, of my investment at a time t years after investing. And this is an exponential function because the unknown is in the power. The base is constant. 1.05 is the base of my power. And I started with 700. So this is slightly more complex than my functions that I looked at before because the previous functions just had a base to a power. They didn't also then times it by another number. But this is more likely what you are going to see. You're going to see a base to a power and then multiplied by a number because it doesn't always start at 1. These original exponential functions all go through y equals 1 because anything to the power of 0 is 1. So if we want to scale it up and start at another number, we need to multiply by the number to start at that number. Okay, so we have now the formula, okay, for the value of my investment. I want to plot this on a graph for t between 0 and 10. So for the first 10 years, I wanted this plotted on my graph. So it would be a good idea to find out what the value of my investment is at 10 years. So when t is 10, v will equal 700 times 1.05 to the power of 10. And that is approximately £1,140. Okay, I'll just put that as 3 significant figures. So plotting it, I don't want an extremely accurate graph. I just want a general sense of the investment over 10 years. So I'm going to plot a very sketchy graph. I don't have a ruler. So here's my very sketchy graph over 10 years. So 5, 10. So I start at 700. I get to 1,140, which is under double 700. So I'll just say that there is 1,000. So 700. So 500 is about there. 700 about there. So I'll start there. And 1,140 is about here. So I'll end there. And I know it's an exponentially increasing, so it'll have a general sort of curve upwards. Okay, that's an appalling curve. I'll try that one more time, but I'll leave it as I have it. So it has a very, very slow curve upwards. 2 to the power of x had a very, very fast curve upwards, but 1.05 is a very, very shallow, only increases by 5% each increase in the x direction. Okay, so the curve will be more gentle, but it's still an exponential. It'll still head upwards. Okay. And over time, it will grow and grow exponentially. So that value there is 1,140 approximately. So there's my plot. So I'll write down here 700, and here it's the v-axis, and here it's the t-axis, where v is the value in pounds, t is the time in years. Okay. So that's my plot. Part C, around what time will my investment be worth £1,000? So I could just attempt to estimate from my appalling graph by drawing a line across at 1,000, going down and reading off. Okay, that's somewhere between 7 and 8. Okay, if that there, around there is 7.5, well, it's a poor graph, but that's 7 and that's 8. So it's somewhere between 7 and 8. So what I'm going to do is I'm just going to now do a bit of trial and error and see if I can get close to the value, which would give me 1,000. Okay, I know it's between 7 and 8. So if I try t is 7, when t is 7, after 7 years, the value, if I plug t is 7 into this formula for my value, I get the value is about £985 to 3SF. If I plug t as 8, so after 8 years, the value of my investment is about £1,030 to 3 significant figures. So I know it's between 7 and 8 years. If I only get the interest at the end of the year, then it would reach £1,000. It would go over £1,000 at the end of the 8th year, and not until then. But if I get paid monthly interest, then I could I could work out a little bit more accurately than just it's after 8 years. I could try 7.1, 7.2 and see whether I got closer. With trial and error, the best value to one decimal place is when t is 7.3 years. So that is the closest that you can get. So around a third of the way, just under a third of the way through the year, I would reach £1,000 for my investment. Okay, 7 years and about a third, just under. Now, in the future lessons, so the next lesson and the one after that, we're going to learn about something called logarithms, which will allow us to calculate this without trial and error. Okay, but for now, we're just going to focus on using trial and error to work out values that would go into this function, which would make the answer we want. Okay, so 7.3 years is as close as we can get through trial and error. Well, we could spend a lot of time and get it much, much closer, but we're not going to do that. Okay, so right now I'd like you to have a go at this question here. At the start of an experiment, there are 5,200 bacteria in each petri dish, in one petri dish. The numbers n of bacteria increase by 20% every hour. I want you to write a formula for the numbers of bacteria n in terms of the time in t in hours after the start of the experiment. Then I want you to plot that on a graph for between 0 and 5 hours. And then I want you to estimate both, if you can see it on the graph, but you may not, and then through trial and error, how long it will take before there are 1 million bacteria in your petri dish, with various assumptions, such as that the petri dish the bacteria don't run out of space in the petri dish. Okay, pause the video, have a go at this question, and then I will show you the answer. Okay, so the answer for this. Firstly, our formula, n is equal to 5,200 multiplied by 1.2 to the power of t, because it increases by 20%, that as a decimal multiplier is 1.2. So after 1 hour, it will be 5,200 times 1.2. 2 hours, 5,200 times 1.2 squared, etc. Plotting it between 0 and 5, I need to have a general sense of how many bacteria I'll have after 5 hours. So when t is 5, the number of bacteria is 5,200 times 1.2 to the power of 5, which is approximately 13,000. Okay, so 13,000 bacteria to two significant figures. So I need my graph, when I plot it, for 5,200 times 1.2 to the power of t, I need a y-axis for n. The x-axis is time in hours. I start at 5,200. I'll end at 13,000. So let's say that 10,000 is there. 5,000 just about there. 13,000. So 15,000 would be there. So 13,000, let's say, is there. Okay. So I know I start at 5,200, just above 5,000. And I know that at t is 5, I'm going to end up at 13,000. And my graph is going to have general exponential growth. So that looks almost like a straight line. I'm going to make it a little bit curvier. It's difficult to do it. And it'll keep going on, okay? So that's my graph for the number of bacteria against the time in hours. I want to estimate how long it'll take before there are 1 million bacteria. Well, my graph doesn't go that far. It only goes up to about 13,000. So I can't read off from the graph. I'm just going to have to do some trial and error. If I try different values of the time in hours, I'll quickly work out that it's less than 30 hours, but more than 20 hours. In fact, if I try t is 28, I get that n, the number of bacteria, is 857,000 to three significant figures. And then if I try t is 29, I get that the number of bacteria is over 1 million. It's about 1,030,000 to three significant figures. So I know it's between 28 and 29 hours later that it reaches 1 million bacteria. In fact, to one decimal place, the best answer is T is 28.8 hours to one decimal place. So if you got close to that, really well done. Okay. In a future lesson, I'll teach you using logarithm how to get that exactly, the exact time at which you get 1 million bacteria. What you should do now is you should practice drawing your exponential graphs and answering questions based on exponentials. The best place to do that is exercise 12.1 from our lovely textbook. It's the first exercise in chapter 12. So off you go and enjoy.